In this video, we solve problem 15.3.026 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The problem statement asks us to evaluate the line integral of f dotted with dr over the path C for each of the paths, which we're going to call C1, C2, C3, and C4. And they give us a hint. They say, remember, if f is conservative, the integration may be easier along an alternate path. Remember, if f is conservative, that line integral is path independent, and we can use the fundamental theorem of line integrals. So we have this line integral stated here. Now, this is in differential form, so it's implied that the function multiplying dx is the x component of our field. If we call our field, or if we label our field in this way, we're going to let f be a field in the plane with components m and n. Then the function multiplying dx is the x component, which we're calling m, and the function multiplying your dy is the y component of our field. And that includes that negative sign, and that's called n. So if this field happens to be conservative, all the calculations are going to be much simpler. Let's test and see if it's conservative. We've got a field in the plane with components 2x minus 7y plus 1, and I'll distribute that negative 7x minus y plus 9. This is my m, and this is my n. Now remember, if we're talking about a field in the plane, a field in the plane will be conservative if the partial derivative of this function with respect to y is equal to the partial derivative of that function with respect to x. So let's check it out. The partial derivative of this function with respect to y is, well, 0, and the derivative of that term with respect to y is negative 7, and the derivative of that term is 0. So just get a negative 7 there. Remember, we're treating x as a constant here when we differentiate with respect to y, so we're just going to get 0. And then over here, we'll compute the partial derivative of n with respect to x. And if those happen to be the same, then our field is conservative. So the derivative of this part with respect to x is negative 7. The derivative of this piece or term is 0 with respect to x because there are no x's in it, and we're treating y as a constant. And then the derivative of 9 is, of course, 0. Since these two partial derivatives are the same, you can use subscript notation if you prefer, that's fine too. So that's equivalent to saying that, and that means that our field f is conservative. And that means our integration over any curve is path independent. So we don't have to take the path that they gave us. And if we're integrating over a closed loop, the fact that this is path independent means that if we start in the same place that we end, well, our line integral is going to be 0. So the answer for part A, where we have the line integral over C1 of f dotted with dr, since f is path independent and we're starting and ending in the same place, the closed loop, we're going to get 0 there. Now in this one, it's a little bit ambiguous the way I've drawn it here. I've tried to make it clear, but maybe not. So I'm going to use my highlighter. Here's my path. We're starting here at x equals 0, y equals negative 1, and then we're going along this semicircle up to x equals 0, y equals 1. And we could take that path if we wanted to. It would be easy enough to parameterize that in terms of sine of t and cosine of t, or using sine of t and cosine of t. But if you wanted to, because this line integral is path independent, you could take the much easier path from this point to this point, and I would recommend that. So rather than doing the line integral over C2 of our function, let's use a different curve. Let's take this path instead. We're going to start down here, and we're going to end up there. So our starting point and our starting point and our ending point are exactly the same. So we're just going to take that path instead. So I will call that C2 star. It's our new C2. So these two guys are going to be equal. Because f is conservative, and we're starting and ending at the same location. And then we can evaluate this integral over that path, which will be relatively simple. That will require us to find a parameterization of C2. So, or C2 star. And I will call my parameterization R of t. It's going to have components x of t and y of t. And I would like you to notice that, we always want to do the simple part first. I'd like you to notice that our x value is 0 the whole time on that line segment. So it's easy to say x of t is going to be 0 no matter what t is. Now I want y to go from -1 to 1. So let's just let y equal t and then require t to go from -1 to 1. And that will give us what we need. Okay, so this is our parameterization of the path. And that means our line integral can be evaluated in this way. Oops. It's the integral from a to b. We're starting at t equals -1, ending at t equals 1, of our field written in terms of x of t and y of t. So my field actually depends on position, but I want to think of it as depending on time. Like if you're a little particle traveling along this path, we're going to be at different locations at different times, and every time we're going to be experiencing a different field. We want to find out what that field would be as experienced by a particle traveling along this path with a position described by this function. Now, of course, it doesn't have to represent, t does not have to represent time, but it's just an easy way for us to think about it. So we're going to take our field, we'll write it in terms of t by making a substitution, and then we'll dot that with r prime of t. So our field was this. Now this tells us everything that we need to do. We need to write our field in terms of t, we need to compute r prime of t, and then we need to take the dot product, and then we need to evaluate the integral. So all the symbols are there, and all the symbols are telling us what to do. This might be a little ambiguous, but if you can remember that this means this, then you're going to be good to go. So let's find our field in terms of t by making a substitution. So when we are on this path, x is equal to 0. So we're going to replace our x with 0. And when we are on this path, as t goes from -1 to 1, y is equal to t, because this is our x component and that's our y component. So I'm just going to substitute in x equals 0, and I'll substitute in y equals t. And then we'll simplify. I'll have -7t plus 1 as my x component of my field, and -t plus 9 as the y component of my field. Easy breezy. So now we need to compute r prime. It's the derivative with respect to t of this vector. That's easy enough. Derivative of 0 is 0. Derivative of t is just 1. And then once you have computed r prime, you just take the dot product of those two guys. We have f dotted with r prime. It's just going to be this component times 0, which of course is nothing, plus this component times 1. And so we get -t plus 9 as our integrand. And we're going to integrate that from -1 to 1 to get the value of the line integral over this path, which is equal to the value of the line integral over that path, because our field is conservative, and that means these line integrals are path independent. So just evaluate this. Bring the -1 down, add 1 to the exponent, divide by the new exponent. Bring your 9 down, multiply by t. The antiderivative of a constant is your constant times your variable. Then you substitute in the bounds, -1 and 1. At t equals 1, we'll have -1/2 plus 9. At t equals -1, we'll have -1/2 minus 9. And if you distribute, you have -1/2 plus 9 minus a minus is going to be +1/2 minus a -9 is going to be +9. These guys reduce and you just get 18. So we just found f, we found r prime, we computed the dot product, f dotted with r prime, and then we evaluate that integral from here to here, and those bounds came from the fact that t went from -1 to 1. Now you could have used different bounds. You could have let t go from 0 to 2, and then this formula for y would be more complicated, but it seemed to me that it would be simplest. I just want to trace this out as t ranges over some interval, and I want y to start at -1 and I want y to end at 1. So if I let y equal t and t starts at -1 and t ends at 1, that's going to give us exactly what we want. So that is how we get that one. That's how we evaluate that. So the answer for the first line integral was 0, because we have a closed curve there. The value of this one turned out to be 18. Evaluating the line integral over this path is the same as evaluating the line integral over that path. Similarly, we could use the path that they gave us here, this exponential function, on part C, but it might be easier to just take the line segment path from this point to this point. If you want to, you could just go along that line. And then r prime is just going to be, since it's a line, the derivative of the x component and the y component are just going to be constants. So it's going to be nice and easy. So I would recommend that we take the alternate path that I've sketched here. If this is C3, I'm going to call this C3 star. And evaluating the line integral over C3 star is going to give us the same value as evaluating the line integral over C3, and because of path independence. So let's evaluate that. This is because f is conservative. And remember what our picture looks like. We're starting at x equals 0, y equals 1, and we're going to x equals 2, y equals e squared. That was the original path, and we're taking this new path instead. We've decided that this is the path that we want to be on instead. And again, I was calling that C3 star. Okay, so we've got a path in the plane, so that means our r of t will have two components, an x component and a y component. And we can think of both of those as depending on time. Now, you can let t range over any range of values that you want, but I find that this is easiest to do, easiest to find, if I let t increase as either x increases or y increases. Now, if y is going from 1 to e squared, like that's not going to be simple. Those won't be integer values for t. So I don't want to do that. I think I'd like to focus on the x values. If I'm on this line segment, x starts at 0 and ends at 2. Since x is going to increase by 2 units, I'll let t increase by 2 units. And then I'll just find the equation for x that causes me, a linear equation for x in terms of t, that causes me to start here when t equals 0 and end over here when t equals 2. So I'll make a little t chart. When x is 0, we want t to equal 0. Whoops. When x is 2, we want t to equal 2. So it looks like x and t are exactly the same. So we'll let x equal t and let t range from 0 to 2. Easy breezy. Okay. Now to find the equation for y, we just need to find the equation of this line. And that's easy enough to do. It's just y equals mx plus b. The y-intercept is 1. So b is 1. And we're going up this many units and to the right 2 units. So if we use rise over run, we're going from 1 to e squared. So that rise is e squared minus 1. The distance from here to here is that y value minus that y value. And then we're running to the right 2 units. So we have y equals e squared over 1, or e squared minus 1 over 2 times x plus 1. So that is y in terms of x when we're on this line, which includes that line segment. If I want the equation for y in terms of t, and I know x equals t, I can just replace the x here with a t, and that's going to give me my y component. So I'll have e squared minus 1 over 2 times t plus 1. And that is the equation of my line, or my line segment, a parametric equation for that line segment, so that as t increases, we're starting here and we're ending up over here. And you can always check, when t equals 0, I get 0 and 1 for my x and y value. When t equals 2, I get a 2 for my x value. And then I have 2 here, so the 2's will cancel, and then I'll have an e squared minus 1 plus 1. The e squared minus 1 and the plus 1, the minus 1 and the plus 1 will reduce, and we'll just get an e squared. So this is giving us what we want. Okay, so now we'll just evaluate this integral pretty much the same way that we evaluated the last one. First, we need f in terms of t. So we need f of x of t, y of t. Because remember, we're evaluating this, which is the same as evaluating the integral from t equals a to t equals b of our field in terms of t. So it's like the field experienced by a particle traveling along that path as t increases from 0 to 2. Just going along, it's experiencing a different field each time. If we're thinking of that as like a force field, just for example, just to give us a concrete way to imagine something that's going on there. And then our dr is defined to be r prime of t dt. So we need the field in terms of t, we need r prime, we need to take a dot product, we need to substitute in the bounds, and of course then we need to integrate. So our field was this, it was -7 times x, 2 times x minus 7y plus 1. Had that wrong in my brain. And then I've got a -7x minus y plus 9. That's f in terms of x and y, but we want them in terms of x of t and y of t. So we just replace x with t, because that's what x is. And we replace y with that expression, which is a lot more involved. It's a line, but because of that e squared, it looks a little funny. That's our x component. Our y component is this. We've got -7 times x minus y plus 9. We're replacing x with t. We're replacing y with e squared minus 1 over 2 times t plus 1. Okay. And I would recommend simplifying this. So let's distribute the 7 here. We've got 2t, let's just say -7 over 2 times e squared minus 1 times t plus 1. Oh, not plus 1. Plus -7 plus that 1, which is going to give us a -6. Then over here, I've got -7t minus 1/2 e squared minus 1 times t, minus 1 plus 9 is going to be a positive 8. Okay, so that is our f in terms of t, and now we need to compute r prime. Okay, so when we compute r prime, we're taking the derivative of t, which is 1, and then we have the derivative of this, this expression with respect to t. That's a constant times t plus 1. The derivative of a constant times t is just the constant. I'll factor out that 1/2 again. So r prime is just a vector with constant components in the x direction and y direction. So these are all vectors that are all pointing in the exact same direction. It's always the same. And that's because we're on this line segment here. And we're sort of traveling along that line segment, at a constant speed. So I've got my f and my r prime. Now I want to compute f dotted with r prime for that right here, that right there. And then we will evaluate the integral from a to b. So if I'm taking this and I'm dotting it with r, this looks much worse than it is. But I have this dotted with 1, or excuse me, this times 1. So it's just going to be that x component of f. And then I have this expression times the 1/2 e squared minus 1. I think I'm going to leave that factored out. Oh, maybe I shouldn't. If I distribute that here, if I distribute that to the negative 7t, I'll end up with a negative 7/2 times e squared minus 1 times t. And then this times that would give me a negative 1/4 e squared minus 1 quantity squared times t. And then that times 8, it's just going to be, well, 1/2 of 8 is 4. So a 4 times e squared minus 1. Okay, and now I've got like terms. I've got one of them over here and one of them over here. So I'm subtracting 7/2 and I'm subtracting 7/2 of them again. So that means I'm actually subtracting seven of them. So this is 2t minus 6. And then these guys, I've taken care of those two. This one and this one together give me a minus 7 times e squared minus 1 times t. And then I've got the minus 1/4 e squared minus 1 quantity squared times t plus the 1/4 e squared minus 1. That's a lot, but it looks more complicated than it is because our variable is t. This e squared minus 1s are just constants. So now we just substitute everything into our formula for the line integral. Basically, it's that one. And we're going to use these bounds for t. T starts at 0 and ends at 2. So I have this 2t minus 6. I think I'll bring that constant over here as well. Plus 4 times e squared minus 1. Take care of that and that and that. And then here I've got minus 7 e squared minus 1 times t and minus 1/4 e squared minus 1 quantity squared times t dt. All right, so first we anti-differentiate. So you bring your 2 down, add 1 to the exponent, and divide by the new exponent. The 2's will cancel. The antiderivative of a constant is that constant times t. The antiderivative of this constant is that constant times t. Now this one has a t in it, so we have to add 1 to the exponent. Well, bring your constant down, then add 1 to the exponent and divide by the new exponent. And here we'll bring our constant down. And then we will add 1 to the exponent and divide by the new exponent. And we evaluate all of this from t equals 0 to t equals 2. At t equals 2, I have 4 there, minus 12, plus 8 times e squared minus 1. And then I'll have negative 7 over 2 times e squared minus 1 times t squared, which is 4. And then I'll have this 1/4 times the 1/2 is a 1/8 times e squared minus 1 quantity squared, and 2 squared is 4. And then when we evaluate all of this at 0, this will be 0, so will this, so will this. Anything that has a t in it will be 0. That's a 0, that's a 0. So everything will be gone. This whole expression will be 0 when t equals 0. So this is our answer. It's just not simplified. 4 goes into 8 2 times. 4 goes into 2 twice. So what we have here is 4 minus 12, which is negative 8, times this quantity. I might distribute that 8. So I'll have 80 squared minus 8. And then here I have a negative 14 times the quantity e squared minus 1. And over here I have a negative 1/2 times the quantity e squared minus 1 quantity squared. So I think I'll just keep distributing. And then at the end, I will collect sort of like terms involving our e squared and our constants. So I'll distribute the negative 14 here. Okay. And so it looks like we've got a negative 8 and a negative 8. That's negative 16 plus 14 is negative 2. So that guy, and that guy are gone. And then we've got 8e squared minus 14e squared. That's negative 6e squared. That guy and that guy are gone. And then we'll take this one and we'll bring him down. There was a math lab tutor that worked for me for a number of years who liked to personify functions by saying this guy and that guy. And sometimes I pick that up, or I remember it and I start using it again because it reminds me of that particular tutor. He was a great tutor. Okay, so that is the value of this line integral. Now we didn't have to do that. We could have also used the original curve. This is y equals e to the x. And that actually may have been simpler. The equations or the antiderivatives of e to the t would have been pretty simple. Okay, actually, I think I want to do that one as well. So let's do that just using the curve that they gave us, because the integration would be simple and show that we get exactly the same thing. So if I am parameterizing that C3 and we're in the plane, so R will have an X component and a Y component. X still goes from 0 to 2, so it still makes sense to let T go from 0 to 2 and just let X equal T. Well, if we're on this curve where Y is equal to e to the X and X equals T, I'll just replace the X with a T and I'll get Y equals e to the T. Yeah, I think this is going to end up being a much simpler integral. Not because the other one was difficult, but because the other one had all those sort of weird constants involving the e squared minus 1. So now let's evaluate the line integral over C3. It'll be the integral from 0 to 2 of our field in terms of t. So we're going to replace x with x of t, replace y with y of t. We're going to dot that with r prime. So that's the plan. We just need to find f in terms of t using this parameterization that we just came up with. So f was originally the field with components 2x minus 7y plus 1 and negative 7x minus y plus 9. And if we're on that path and we use this parameterization, x is given by t. So I'm replacing all of my x's with t's. Oops, excuse me. And y is given by e to the t. So I'm replacing all of my y's with e to the t's now. So I have negative 7 times x, which is t, minus y, which is e to the t. I'm adding 9 to that. So that's my field F. And then after we find our field f, we want to compute r prime. And since the derivative of e to the t is so easy, r prime is easy to find. The derivative of t is 1. Derivative of e to the t is e to the t. And then, just like this says, we want to take our field and we want to dot it with r prime. The formula really tells us how to do this. It tells us everything. This version of the formula. If you see this, you have to think of this, because in order to evaluate this, we need to write everything in terms of t. And t does not have to represent time, but one way that you can think about this is you can think of t representing time. You've got a particle traveling along this path. They're going to be at different positions at different times, and therefore they're going to experience different fields at different times. We want to take that field that the particle is experiencing, and we need to dot it with the velocity vector. Okay. So f dotted with r prime is just this times 1, which is of course just 2t minus 7e to the t plus 1. And then it's this expression times e to the t. So I'll just write all of that down. So it should be a minus. And multiply by e to the t. And I will distribute there as well. So we'll have negative 7t times e to the t. A negative e to the t times an e to the t is going to be a negative e to the 2t. We're adding the exponents. And then we've got a 9e to the t at the end. So these guys are like terms, the negative 7e to the t and the 9e to the t. So it's going to be 2e to the t. Bring that 1 down. And this guy, when we anti-differentiate, we'll need integration by parts. And this one is a pretty straightforward KT substitution for our anti-differentiation rules. Okay, so that's our f dotted with r prime. Now we will set up and evaluate the line integral. And we should get exactly the same answer that we got using the other method. So we'll have the integral from 0 to 2 of this. And I think I will include all the terms that are easy to handle first over here. And then I'll leave the negative 7t e to the t for a separate integral, because we'll use integration by parts for that. So let's evaluate the integral of each of these pieces first. Bring your constant down, then add 1 to the exponent and divide by the new exponent. Bring your constant down. The antiderivative of e to the t is e to the t. The antiderivative of 1 with respect to t is t. The antiderivative of e to the kt with respect to t is e to the kt, and you have to divide by k. So we'll have a 1/2 here. And we want all of that evaluated from 0 to 2. And I'll factor out, actually, I don't think I'll factor out the negative 7. Then I want to add the integral from 0 to 2 of this guy. Now, this requires integration by parts. You can use traditional integration by parts, but whenever I have you use a polynomial with integration by parts, I like to use the tabular method because it's nice and simple. Since I've got a polynomial times e to the t, I'll let u be my polynomial. I'll let dv be everything else. And I'll use tabular integration. So you put your d or your u over here and your dv over here, and you sort of ignore the dt. And then in this column, you differentiate until you get 0. So you get a negative 7 and then a 0. And in this column, you anti-differentiate. It's just easy enough because we're dealing with e to the t. And then you've got these signs. Now, according to tabular integration, the antiderivative of this is this times this, times positive 1, plus this times negative 1. So what we're going to have here is a negative 7 e to the t, a negative 7t e to the t minus a negative 7. So it's going to be plus 7 e to the t evaluated from 0 to 2. Okay, so that's that piece. And then we have whatever we get over here when we substitute in t equals 2 and t equals 0 and subtract. When t equals 2, we get 4 plus 2e squared plus 2 minus 1/2 e to the 4th. When t equals 0, this is 0. We have 2 times e to the 0, which is 1. 2 times 1, which is 2. And then when we substitute t equals 0 here, we have 0. And then on the last one, we'll have 1/2 e to the 0, which is a 1/2 times a 1. So this is 6 plus 2e squared minus 1/2 e to the 4th. And this is 4 halves. 4 halves minus 1/2 is 3 halves. Subtracting 3 halves. If you want, you could write this 6 as 12 over 2. And if you combine the 12 over 2 and the negative 3 over 2, that means we're going to have a 9 over 2 there. Okay, so that's that. And then we have this piece over here. If we evaluate at t equals 2, we'll have negative 14e squared plus 7e squared. And if we evaluate at t equals 0, with negative 7 times 0 times something is just 0. Plus 7 times e to the 0 is 1. So we have a negative 14e squared plus 7e squared, which is going to give us a negative 7e squared there. And then here we'll have a minus 7. Okay, so we can multiply that one by 2 over 2 to combine it with this 9 over 2. So we'll have 9 over 2 minus 14 over 2 is negative 5 over 2. Then we have the 2e squared minus 1/2 e to the 4th minus the 7e squared. And these guys can be combined. So you have negative 5 over 2. If I've got 2 of those and I'm subtracting 7, that means I have negative 5 of those. And then I have the negative 1/2 e to the 4th. Okay, so this answer looks a little different from the last one, but I bet they're equivalent because this says, what do I have to do here? I have to write this twice in FOIL. The last term is going to be a positive 1. I'm going to have the positive 1 times the negative 1/2. The negative 1/2 and the negative 2 is going to give me that negative 5 halves. And I've got a negative 6e squared in there, but that's going to cancel with I think, a positive 1e squared that will come out of this to give us the negative 5e squared. And then e squared times e squared, that would be first times first from this. That's going to be e to the 4th times the negative 1/2, and that ends up being that right there. So you can use an alternate path if you don't want to integrate over e to the x, which I thought would be a good idea because derivatives of linear functions are just constants. But it just looked kind of messy because we had these e squared minus 1s everywhere. If we used the path that we were given, the parameterization was relatively simple and the integration was relatively simple. We just needed to add in a little integration by parts at the end, which isn't too bad at all. Okay, so that is C. We took care of that one. And this last one is a closed path. Again, our field is conservative. It's saying start here, go up here, and then come back down, and you are exactly where you started. So the line integral over C4, since it's a closed path, that's going to be 0. And it's not just because it's a closed path, it's because it's a closed path and our field is conservative that we get 0. So you have 0 for this one, 0 for the top one. And on this one, it was easier to choose an alternate path. And on this one, I thought it might be easier, but it actually was easier to use the original path that they gave us. So I hope that helps. Please let me know if you have any questions.